Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to solve another nice problem. Let me write the problem, then we will discuss the solution together. So today's problem goes like this. A charged drop of oil of radius r equal to 2.76 micrometer and density rho equal to 920 kg per cubic meter is maintained in equilibrium under the combined influence of its weight and a downward uniform electric field of magnitude E equal to 1.65 into 10 raised power 6 Newton per coulomb as shown in figure 1. We will draw the figure. Then the question says, part A of the question, calculate the magnitude and sign of the charge on the drop. Express the result in terms of the elementary charge E. Then we have Part B, the drop is exposed to a radioactive source that emits electrons. Two electrons strike the drop and are captured by it. Let me change the color. Changing its charge by 2 units. If the electric field remains at its constant value, calculate the resulting acceleration of the drop. This is our problem. Let me draw the figure first. Figure is like this. These are the plates of a capacitor to establish the electric field. Now between these plates there is electric field pointing downward. So we have electric field E pointing downward in this space between the plates, right? Now we have this. Let me use another color. This is our oil drop. Let this be our y-axis, and we take upward direction as positive. Now it is acted upon by weight. That weight is mg, acting downward, where g is the acceleration due to gravity, m is the mass of this drop, and let me use another color. It is acted upon by the electric force due to the electric field, and that force is QE. right? So this is our figure 1. We have electric field between the plates of a capacitor. Electric field is downward. Oil drop is placed inside it, and that is kept in equilibrium under the action of the electric field acting downward and the gravitational field acting downward. Y direction we have taken positive in upward direction, right? So let us check the problem before going to the solution. So a charged drop of oil of radius r equal 2.76 micrometer and density rho equal to 920 kg per cubic meter is maintained in equilibrium under the combined influence of its weight and a downward uniform electric field E equal of magnitude E equal to 1.65 into 10⁻⁶ Newton per coulomb, as shown in figure 1. Part A, calculate the magnitude and sign of the charge. Sign of the charge on the drop. Express the result in terms of the elementary charge E. Then part B goes like this. The drop is exposed to a radioactive source that emits electrons. 2 electrons strike the drop and are captured by it, changing its charge by 2 units. If the electric field remains at its constant value, calculate the resulting acceleration of the drop. So let us move to the solution. First, we take up part A. Now, to keep the drop in equilibrium, its weight mg must be balanced by an equal electric force of magnitude QE. We know mg is weight and QE is the force experienced by a charged particle Q in an electric field E. And we know the electric force experienced by a charged particle is in the same direction as that of the field if the charged particle Q is positive. If the charged particle is negative, then the force experienced by it in the electric field will be oppositely directed to the electric field. We know it. Now, because the electric field is given as being in the downward direction, the charge Q on the drop must be negative for the electric force to point in a direction opposite the field. I repeat, weight is downward. It is given that electric field is upward, and it is also given that the oil drop is in equilibrium. That means electric field must be upward, and for electric field to remain upward, the sign of the charge on the oil drop must be negative. The one conclusion is the charge Q on the drop must be negative, right? This is our first conclusion about this problem. Now we want to find the sign of the charge. We can use the equilibrium condition. Let me use another color. Now, equilibrium condition is net force acting on the drop is 0. There are two forces. One is mg plus QE. Electric force and weight, they must sum up to 0 because the drop is in equilibrium. Now taking y components, we take y components of the vectors, acceleration due to gravity, and the electric field, but we obtain minus mg plus q into minus e is equal to 0. Because electric field, y component of the electric field is minus c because whole electric field is pointing downward, and y component of the acceleration due to gravity is minus g, right? So we have minus mg plus q times minus c is equal to 0, or solving for the unknown q, we have q is equal to minus mg over e minus mg over e. Now how to find the mass of the oil drop? G we know, E is also given. How can we find the mass? Simple. We know density is mass over volume. So mass is density times volume, right? So density is given in the problem. Density is given. This is the density of the oil drop, and its radius is also given. So we can find the mass. So we reach here. Q is equal to minus, instead of m, we will write volume times the density. So volume is 4 by 3 pi r cube, because the oil drop is spherical in shape. Volume of the sphere is 4 by 3 pi r cube times the density times the acceleration due to gravity over e. Then check it. Q is minus mg over e. Instead of m, we have written volume times density. Volume is 4 by 3 pi r cube. Rho is density, g is acceleration due to gravity. So let us put the numbers. Let me use red color. So we have minus in front. Then we have 4 by 3. Then we have pi. Then we have r cube. R is 2.76 into 10 raised power minus 6 meter. Then we have Q. Then we have the density, which is 920 kg per cubic meter. Then we have the acceleration due to gravity, 9.8. meter per second square, and we have E, which is 1.65 into 10 raised power 6 Newton per coulomb. Let me check it. Minus 4 by 3 pi times 2.76 into 10 raised power 6 meter. It was given that radius of the drop is 2.76 micrometer, and remember 1 micrometer is 10 raised power minus 6 meter. So we have used that 2.76 into 10 raised power minus 6 meter, and there is cube outside. Then we have density 920 kg per cubic meter times the acceleration due to gravity 9.8 meter per second square divided by the electric field 1.65 into 10 raised power 6 Newton per coulomb. So when we calculate these numbers, it turns out to be minus 4.8 into 10 raised power minus 19 coulomb. As always, we need to check the calculation. Check the calculation at home. So we have solved for the magnitude of charge on the oil drop, which is 4.8 into 10 raised power minus 19 coulomb, and its sign is negative. Now, second portion of the part A says express the result in terms of the elementary charge E. You know, the elementary charge E stands for 1.602 into 10 raised power minus 19 coulomb. So we want to express this charge in terms of E. So let us do that. So we can write Q as N times minus E. Because it is negative, we want to write how much, what is the number of elementary charge contained in this amount of charge, right? Minus E is the charge on the electron, E is the charge on the proton. So if Q is the charge on the drop, we write it N times minus E. N is the number of electronic or elementary charges on the drop. Then what is N? N is Q by minus E. Let us put the numbers. Q is minus 4.8 into 10 raised power minus 19 coulomb. Minus E is minus E is 1.6 into 10 raised power minus 19 coulomb. Q is minus 4.8 into 10 raised power minus 19 coulomb is 1.6 into 10 raised power minus 19 coulomb. When we solve it, it turns out to be 3. Let me encircle it. So conclusion is that the charge on the drop is 3 electronic charges or 3 elementary charges, right? So this completes our part A. Let us move to the solution of part B. Let me refresh first your memory what part B says. Part B says the drop is exposed to a radioactive source that emits electrons. 2 electrons strike the drop and are captured by it. So when the drop captures 2 electrons, its charge will change by 2 units. But the electric field is maintained constant. Now, equilibrium will not remain, equilibrium will be disturbed. So drop will experience acceleration because the electric force on the drop will change, weight is constant. We have to solve for that acceleration using Newton's second law. So let us move. Now, if we add two additional electrons to the drop, its charge will become, we call it Q prime. First we called it Q, which was 3 electronic charges. Now Q prime is n plus 2 times minus e, because it has absorbed 2 electrons. Charge on 1 electron is minus e. First it had n, which turned, so it n plus 2 will become 5, because n was 3. Now it has absorbed 2 electrons, so its new charge Q prime is n plus 2 times minus e, which is 5 times e is minus e is 1.6 into 10 raised power minus 19 coulomb. Minus 1.6 into 10 raised power minus 19 coulomb. When we solve for it, it is minus 8.0 into 10 raised power minus 19 coulomb. So this is the charge of the oil drop after capturing 2 electrons, minus 8 into 10 raised power minus 19 coulomb. Now we have to solve for the acceleration. Therefore, we will make use of Newton's second law. Net force is equal to mass into acceleration. So let us write that. Newton's second law is net force acting on the drop, which is vector sum of two forces, mg plus q prime e must be mass times the acceleration. Remember, when we wrote Newton's second law in part A, we equated it to 0 because the drop was in equilibrium, its acceleration was 0. Now equilibrium is disturbed, it has acceleration, and we have to solve for that acceleration. So we wrote net force is equal to mass times acceleration. Net force is sum of two forces, weight mg and q prime e, which is the electric force. Now again, taking y components, taking y components of the forces, we obtain minus mg plus q prime into minus e is equal to mass into acceleration, because acceleration is also in y direction. There is no x component for acceleration. E is minus, we've already discussed that, because electric field is pointing along negative y direction. Same goes true for gravitational acceleration g. So we have minus mg plus q prime minus c is mass times acceleration. We're not sure about A. We have not written any sign for A. That will be decided by the solution, whether A is negative or positive. Solving for the acceleration, let me use another color. Sorry. Solving for the acceleration, when you solve, it is A is equal to minus G minus Q prime E over M. When you solve for A, you will get this minus G minus Q prime E by M. Let us put the numbers. Minus 9.8 meter per second square minus Q prime. Let me use here another color. Q prime is minus 8.0 into 10 raised power minus 19 coulomb. Then I have E, which is 1.65 into 10 raised power 6 Newton per coulomb, right? Then downstairs we have mass, which is volume times the density, which is 4/3 pi r cube. R is 2.76 into 10 raised power minus 6 meter. And then there is cube outside, multiplied by the density, which is 920 kg per cubic meter. Let me use another color here. So when I solve it, it turns out to be minus 9.8 meter per second square plus, this term will become plus because here is one minus and you have here minus in front. Minus times minus is plus, plus 16. Let me write it neatly. Plus 16.3 meter per second square. When I solve it, A will turn out to be plus 6.5 meter per second square. Let me check it first. Minus 9.8 meter per second square minus Q prime minus 8 into 10 raised by minus 19 coulomb times E 1.65 into 10 raised by 6 Newton per coulomb divided by mass, which is volume times density. Volume is 4/3 pi r cube. R is 2.76 into 10 raised by minus 6 meter. Then we have cube times 920 kg per cubic meter. The value of the second term is plus 16.3 meter per second square. First term is minus 9.8 meter per second square. When we make the calculation, it turns out to be plus 6.5 meter per second square. Since the value is positive, that means the drop accelerates in the positive y direction. So conclusion is, let me use this color. The drop accelerates in the positive y direction. In the figure, that means in the upward direction, right? This completes the solution of the problem. Now, one remark is in this calculation, we have ignored the viscous drag force, which is usually quite important in this situation. We have in effect found the acceleration of the drop at the instant it acquired the extra 2 electrons from the radioactive source. The drag force, which depends on the velocity of the drop, is initially 0 if the drop starts from rest. You know, drag force is velocity dependent force, but the drag force increases as the drop begins to move, and so the acceleration of the drop will decrease in magnitude if we consider the drag force, right? So let me summarize the problem. So first we concluded the sign of the charge on the drop to be negative. We said F is QE, electric field is downward. For the electric force on the drop to remain in upward direction, charge must be negative, which we obtained from Newton's second law. And the sign of the charge we obtained, size of the charge we obtained as this number. Then we expressed this charge in terms of the elementary charge. Then we made the change in the charge. We added 2 additional electrons to the drop mathematically, and its charge is now Q prime. Then we use Newton's second law to find the acceleration of the drop, and we ignored drag force. So I hope you enjoyed this problem and all the problems you are enjoying and noting and trying them. And here you have an assignment. As always, check the calculation at home. This is all for today. Don't forget to like, share, and subscribe my channel. You can give comment in the comment box. Thank you. God bless you. Assalamu alaikum.